All right, welcome to 6.1 Projectile Motion. Just a reminder that 6.1 is going to be broken into two different videos, so you will have to watch two videos to watch 6.1. This is part one of part two, or of two parts. So chapter 6, we are talking about projectile motion. We've been talking about kind of forces in chapters 4 and 5, velocity and acceleration in 2 and 3. Well, now projectile motion is just kind of the next step in the book. In projectile motion, we have to deal with angles. So now, before, we've been dealing with everything in 90-degree angles. I'm rolling a ball on the floor, or I'm running in a straight line. And projectile motion is a little different. So when we talk about projectile motion, two pieces of vocabulary to get a hold of. First off, a projectile, which hopefully all of you know is a launched object. And then a trajectory is the path that object takes. Now, if we want to talk about trajectories, it's just on the bottom here, probably one of the most famous trajectories in the history of mankind. Here's the trajectory that Apollo 11 took to the moon. All right, Apollo 11 is definitely a projectile since it was launched by a rocket. So just kind of an idea. Now that's a complex trajectory. We are going to be studying simple, a lot more simpler trajectories than launching a rocket into outer space and landing on the moon. So when we talk about launching projectiles, all right, we have to talk about two directions. We have to talk about X and we have to talk about Y. And when we do that, we're going to break everything down into X and Y motions. So the shape of the trajectory depends on your frame of reference. All right, if I'm standing underneath the ball, I may throw it straight up. Right. However, if I'm standing to the side, that ball might go out and the wind may blow it back, but from my perspective, it might go up and down. From someone from a side perspective, that trajectory might look a little different. So trajectory depends on reference. So when we talk about frame of reference, we are talking about X and Y. So when we talk about horizontal and vertical, so horizontal is our X value, horizontal is our X, and vertical is our Y. And we're going to break everything into X and Y values. So when we talk about the horizontal component, we're really finding position. Now the equation is no different than what it is when we talked about velocity and acceleration in chapter 2 and 3. All right, so when we break down the equation for finding the X, all right, X is equal to Vx times t. Now, since we're breaking everything into X and Y dimensions, we have velocity in the X and Y direction, and distance is really just X. Now, we go through X is equal to Vx times t. X is a horizontal displacement. Vx is the initial horizontal velocity, and t is time. Now, you might remember seeing this equation earlier in the year. Distance is equal to velocity times time. Same exact thing. Distance is really x, but it's your distance in the x direction. Velocity is our velocity now in the x direction. And time still stays the same as time. So that is what we're going to break our x component into if we need to solve for distance in the x direction or velocity in the x direction. That is the equation we're going to use. When we break down and look at vertical motion, all right, or our y direction, all right, now anytime you throw an object up, all right, vertically, you have to deal with gravity. So we are going to have gravity as a part of this equation. All right. You can use multiple equations to find the motion of a projectile, but when you do it, essentially you're going to have two equations. Right. Y is equal to Vyt plus 1/2 gt squared, or Vyf is equal to Vyi, should be Vyi, plus gt. And we're going to spend most of our time dealing with the first equation, but there is an occasion where you might use the second equation. But very similar to what we've done with velocity and acceleration equations already. All we're doing is instead of d, now we're plugging in y, and then we're talking about distance in the y direction. And now instead of plugging in just velocity, we're plugging in Vy, which is velocity in the y direction. And then a 1/2 gt squared is the same. So we have direction the x and the y. Now, just like we were talking about when we did the equation with, just a second here. So we look at this problem here. We have a stone is thrown horizontally at 15 meters per second from the top of a cliff that's 44 meters high. How long does it take the stone to reach the bottom of the cliff? So we are looking for time. All right. And we are given two pieces of information. We are given 15 meters per second, and we are given 44 meters high. Well, the stone is thrown horizontally at 15 meters per second. So is that going to be Vx or Vy? It'll be Vx is 15 meters per second, and y is equal to the height of the cliffs, 44 meters. Right. So now we are trying to go and look for, we're trying to look for time. Well, for time, we have two options for equations. We could do the x is equal to Vx times t. That equation has time. Or we can do the y is equal to Vyt plus 1/2 gt squared. Now, we got to look at those equations. Do we have x? Is x given to us in the problem at all? No, it is not. So we cannot use the first equation since we don't have x. Let's look at the second equation. Y is equal to Vyt plus 1/2 gt squared. We have y. Vy, well, the stone is thrown completely horizontally down the x-axis. If it's thrown straight down the x-axis, is there going to be any y velocity? The answer is no. There will be no y velocity. So Vy is 0. We're solving for t and we know g. So we can go ahead and use this equation. Let's plug everything in. Y is 44. Vy we know is 0 times t plus 1/2 9.8 times t squared. Simplify this equation mathematically. We get 44 is equal to 4.9 t squared. 0 times t was 0, and then 1/2 times 9.8 is 4.9. We're going to divide by 4.9, divide by 4.9. And when you take 44 divided by 4.9, you end up getting 8.97. T squared is equal to 8.97, square root. And in this example, our time ends up being with sig figs 3.0 seconds. All right. So we're going to use one of those two equations and we're going to solve for time. Next up then, B. How far from the base of the cliff does the stone hit the ground? Well, if we have a drawing here, all right, here's my cliff. I'm standing on top of the cliff and I just threw a rock off. And it's going to hit the ground like that. How far from the base of the cliff? So we are looking for this distance. Well, what is this distance? That distance, is it distance in the x direction or y direction? It's distance in the x direction. So now we're going to have to solve for x. Well, we know t from the previous example was 3.0, and then the initial problem, Vx was 15. So x is equal to Vx times t. That's equal to 15 times 3.0. 15 times 3.0, x equals 45 meters. So the base of the rock was 45, or the rock fell 45 meters from the base of the cliff, what we just solved for. So what we essentially have is you have x and y, and you have to figure out x and y. Now we just did simply throwing in the x direction or simply throwing in the y direction. In part 2, we're going to talk about, well, what if I throw at an angle? Well, then we have to break it into x and y. So here initially it was broken into x and y. Next up, we're going to talk about we have to solve for x and y using angles. So that'll be part 2 of 6.1.